Okay, so now we're going to talk about sequences and their convergence, all right? So a sequence whose terms approach a limiting value is said to converge. So basically what that is saying is if you can find a limit for your sequence, then you can say the sequence converges. So sequence convergence is synonymous with being able to find a limit. Now, because a sequence is really just a function whose domain is restricted to the set of natural or counting numbers, if you can find a function that matches up exactly with your sequence and find a limit for that function, then you found a limit for your sequence also, because your sequence is going to match up with that function at every positive integer. So that's what this theorem says. So here's the definition of convergence. Just being able to find a limit means that the sequence converges. Now here's a theorem. The theorem says let L be a real number and let f be a function of a real variable, such that the limit of f of x is equal to L. Notice this is a function of a real variable. So the domain of this function that we're talking about here, the f of x, is the set of real numbers, not the set of natural or counting numbers. So this f of x that we're talking about up here is not the actual sequence. But we do have a function that when we take the limit as x approaches infinity, we get the limit L. We get the limit to be L. Now, if an, which is the sequence, so if the sequence is a sequence such that f of n, notice it's not the f of x, f of n, where n is going to be an element of the set of counting numbers, is equal to a of n for every counting number n. So basically, this is the function that if you restrict the domain to the set of counting numbers, you get the sequence an. That's what the function f is. And all this is saying is that the limit of the function is equal to the limit of the sequence. So if you know how to find limits, basically this theorem is saying if you already know how to find limits, then finding the limit of a sequence is the same as finding the limit of a function. That's what this is saying. So let's go ahead and find some limits for some sequences. And if we can find a limit for the sequence, then we can say that the limit or that the sequence converges. So let's go ahead and do that. Well, let's see here. The first example I'm going to look at is this sequence. This is the nth term. The nth term of this sequence is going to be 3n over the square root of 4n squared minus 3. So here's a sequence, and I want to determine if the sequence converges. So that's the question. Does this sequence converge? Well, in order to find out if this sequence converges, I need to find a limiting value, or basically I need to find the limit. So let me go ahead. I'm going to take the limit as n approaches infinity of an, which is equal to the limit as n approaches infinity of this expression. Now, if you remember, when you're taking a limit at infinity, what you're really looking for is a horizontal asymptote, or a limiting number. And in order to do a problem like this, the first thing you do is you plug in infinity, and you realize that you get infinity over infinity. From there, there's a few things you can do. Since you get infinity over infinity, we could apply L'Hopital's rule, but there's a little bit of an easier way of doing it here. L'Hopital's rule will work, but at one point in Calc 1, we learned a method of dividing everything by the highest power and then taking the limit. So let's try that method. So the highest power of n that I see anywhere is n to the first power, because here's an n to the first power, and the square root of n squared is also n to the first power. So what I'm going to do is I'm going to divide everything by the highest power of n I see, which is n to the first. In the numerator, I'm dividing by n. In the denominator, I'm actually going to divide by the square root of n squared. Now, because n is a set of counting numbers, I don't have to worry about the absolute value here, because I know that n is positive, so that the square root of n squared will just be n itself, not the absolute value of n. And I'm going to go ahead and I'm going to divide everything by n to the first power. On top, I'm actually going to divide by n. So it's going to be 3n over n. But on the bottom, I'm actually dividing by the square root of n squared, which is equal to n. So I'm dividing the top and the bottom by the same thing. So the bottom is going to be 4n squared minus 3 over the square root of n squared. So I get this. This is equal to the limit as n approaches infinity of, well, 3n over n is just 3. And in the denominator, I get this. I can combine these all into one fraction, 4n squared minus 3 over n squared, in which case I can split the denominator amongst both of these terms. So I get the limit as n approaches infinity of 3 over the square root of, this is going to be 4n squared over n squared minus 3 over n squared. And let's see, 4n squared over n squared is just 4, so I get this is equal to the limit as n approaches infinity of 3 over the square root of 4 minus 3 over n squared. And then taking this limit, if you take this limit as n approaches infinity, well, the only thing that involves n is this term, and as n gets larger and larger and larger, this term tends towards 0. So this limit is actually equal to 3 over the square root of 4, or 3 over 2. So there, the answer is yes. Yes, this limit, or yes, this sequence converges, and it actually converges to the number 3/2. So the sequence converges, and it converges to 3/2. All right, let's take a look at another example. Let's take a look at the example where an is actually equal to, let's say, x squared plus 3 over x plus 1. Okay, the question here again is, does this converge? Does this converge? Well, let's see. That means I'm looking for the limit as n approaches infinity of an, which is equal to the limit of this thing as n approaches infinity of x squared plus 3 over x plus 1. Once again, I can use the same trick from Calc 1 where I just look at the highest power of x that I see and divide. Oops, these shouldn't be x's. My fault. We're restricting this to the set of natural numbers, so these are actually n's. I'm sorry about that. An is actually a function of n, natural numbers. So all the x's that were up here I changed to n's. Okay, so an is n squared plus 3 and over n plus 1. So I get the limit as n approaches infinity of an is actually equal to the limit as n approaches infinity of this. So what I'm going to do here is I'm going to go through and use the same trick that I learned from Calc 1, and I'm going to go ahead and divide all of those by the highest power of n that I see. The highest power of n I see is n squared. So I'm going to divide everything by n squared, all the terms. So I get the limit as n approaches infinity of n squared over n squared plus 3 over n squared. I'm dividing by the highest power of n. N over n squared minus 1 over n squared. I divide every term by the highest power of n that I see, which is n squared, which gives me the limit as n approaches infinity of, well, let's see, n squared over n squared, that is 1 plus 3 over n squared divided by n over n squared is 1 over n, and then minus 1 over n squared. Now, upon taking the limit, let's see what happens. Well, as n approaches infinity, this term goes to 0. Because you're dividing 3 by infinity, which gives you 0. As n approaches infinity, this term also goes to 0. Because you're dividing 1 by infinity. And this term also goes to 0. So what you get is, this is actually equal to 1 over 0, which is infinity, or undefined. So therefore, since we cannot find a limit, this means the limit does not exist. Limit does not exist. And since the limit does not exist, that means that this sequence does not converge. This sequence diverges. So this sequence diverges. So we've seen an example where the sequence converges when you can actually find the limit, And we've seen an example here of when the sequence diverges. When you get an infinite limit, the limit does not exist. All right, let's look at one last example. And the example I want to look at is where an, because I've been dealing with algebraic functions so far, and algebraic functions, whenever it's an algebraic function, you can use that trick. But what about if one of your functions is transcendental, like the natural log? So we have this. Well, let's see. We're going to do the limit as n approaches infinity of the natural log of the square root of n over n, and direct substitution yields infinity over infinity. So that's it, one of the indeterminate forms. So I have to do something else to find this limit. I can't determine what the limit is based on just direct substitution. Well, it turns out that whenever you get infinity over infinity, that indeterminate form, you can use L'Hopital's rule to calculate this limit. So let's see, or we can at least try to use L'Hopital's rule. But first, before I do that, I want to rearrange this algebraically. So I have the limit as n approaches infinity, and I'm going to write this as the ln of n to the 1/2 over n. And because this is a natural log function, I can bring the 1/2 to the front. So I get the limit as n approaches infinity of the natural log of n over 2n, because I can bring the 1/2 to the front and multiply it. And then I get that expression. Well, if I plug infinity into that expression, I still get infinity over infinity. So that I can still use L'Hopital's rule on. And L'Hopital's rule says that this, well, if this limit does exist, then, or sorry, if the limit as n approaches infinity of the quotient of the derivatives exists, then it's equal to that limit. So I first have to figure out if the limit of the quotients exists, of the quotients of the derivatives. So I'm going to look here, and I'm going to find the quotient of those two derivatives. Well, the derivative of the natural log of n is 1 over n. And the derivative of 2n is 2. So if this limit exists, then it's going to be the same as that limit. So let's see. This is the limit as n approaches infinity of 1 over 2n. And if I take this limit, I get this limit is equal to 0. Which means, since this limit exists, the limit as n approaches infinity of the quotient of the derivative, since that limit exists, that means that this limit also exists. That means that this limit also exists and is equal to the same thing. So there you have it. That limit converges, and it also converges to 0. So that's how we deal with convergence of limits, or convergence of sequences.